Hey everyone, I'm Nick, and this is Bits of Architecture. So in this episode of the series, we're going to be talking about the basics of integer arithmetic with our binary numbers. So in the last video, we looked at how we can represent our positive and our negative integers in binary, but it's important that we also know how to do some basic arithmetic with these numbers. So starting out, we're going to talk about negation. So how do we go, say, between the positive and negative form of some binary number? So say go between 4 and -4, or vice versa. Now, from a purely mechanical perspective, the operation is just two simple steps. So the first thing we do is we flip all the bits. So all the zeros become ones and all the ones become 0. And then we add 1 to that final result. So for example, going between 4 and -4 and a 4-bit number here. So 4 is just 0, 1, 0, 0. The first thing that we do is we flip all the bits. So 0, 1, 0, 0 becomes 1, 0, 1, 1. And then we add 1 to that result, and that gives us 1, 1, 0, 0, right? Our expected result here. And it also works the opposite way. So we could start from -4 and go back to 4. So we would just flip all the bits, same as before. So 1, 1, 0, 0 turns into 0, 0, 1, 1. And then we just add 1 to that result. So 0, 0, 1, 1 plus 1 is 0, 1, 0, 0, which again is 4. So we can do it either way, from positive to negative or from negative to positive, the exact same two steps. Now, how exactly does this work, and why does this work? Well, the idea behind this is the idea of a complement. So we want the positive and negative of a number to add up to 2 to the n in this case. And this is an idea called a radix complement, or more specifically in our case, a 2's complement. So you may hear the sign representation referred to as 2's complement numbers. This is pretty much what every single computer uses today. And this actually idea goes back a long time, back to the John von Neumann's seminal paper on the first stored program computer, where he talked about using this as a form of representing our signed binary numbers. So how exactly does this process give us these results that when we add together get us to 2 to the n? Well, let's think about it from a practical example. So say we have binary number 001 here. So if we flip all the bits of this number, right, we get 110. And if we add those two values together, we get all ones. So we just get 111. And we're talking purely from an unsigned perspective, getting to 2 to the n. So we know from talking about range in our last video that if we have all ones for n bits, that gives us a value, an unsigned value, of 2 to the n minus 1, right? That's our max range for an unsigned number of n bits. And that's what we get from flipping all the bits and adding those two numbers together, right? The pre-flipped and the post-flipped. So we're really one away from this 2 to the n number, right? We're at 2 to the n minus 1. So that's why we do this extra addition, right? That second step of this two-step process of flipping all the bits and then adding 1. And that gives us the 2's complement of a number. Okay, so that's kind of a little bit of the theory behind it. I would encourage you to look up things like radix complement and 2's complement if you want to know a bit more about that theory and the derivation of how that works. Okay, so moving on, another operation that we often perform or think about is this idea of sine extension. So we have a value, say, represented in 4 bits, and we want to see what that value looks like in 5 bits, or maybe in 16 bits, or maybe in 32 bits. So we want the exact same value, but with more bits. So how does this work with our signed numbers? So how do we extend the number of bits of a signed number? Well, it's pretty simple. It works the exact same way for both our positive and our negative numbers. All we need to do is continuously add the most significant bit, or rather the sign bit. We just copy whatever that bit is, however many times we need. So for example, with our positive numbers, right, going from 4 bits to 5 bits, right, if our most significant bit is a 0, we just copy the 0 one time. Likewise with our negative numbers, right, so here we have -8, so 1, 0, 0, 0. To go from 4 bits to 5 bits and still represent -8, we just copy the most significant bit, our sign bit. So now we have 1, 1, 0, 0, 0 instead of 1, 0, 0, 0. But how exactly does this work? Now, I think the positive number case is fairly intuitive. If we just add 0 to the front of a number, it does not change that number whatsoever. It does not make it any larger or any smaller. We've just added 0 to a number. So, of course, our final result stays the same for however many bits we have. But how exactly does it work for our negative numbers here, right? So let's think about it in terms of what these digits represent, right? So our most significant bit is our sign bit. So that's going to always represent either 0 times 2 to the n minus 1 or negative 1 times 2 to the n minus 1 for our sign numbers. So in the case where we add an extra 1, right, what we've done is we've added, we now have negative 2 to the n minus 1 here. So in the case of 5 bits, that's going to be minus 16. But we still have that original bit here, right, that used to be our sign bit or our most significant bit. And now that's just gone from being negative to now being positive because it's no longer the most significant bit. So here, while we've doubled the value of our negative number, right, to negative 16, we've also added half of it back, right? So now this is positive 8. So it's, in our 4-bit case, we just have minus 8 plus 0 plus 0 plus 0. And now we have minus 16 plus 8 plus 0 plus 0 plus 0. So basically every time we copy that sign bit of a negative number, we're doubling the negative number, but we're taking half of it away because we're adding back half of it as a positive value, right? So that's why it works for our negative numbers here. We're doubling the negative part, but then halving it, right? Because we're adding half of it back. Okay, so that's a bit about how Sine Extension works. Now let's get into how we add binary numbers together, so some simple arithmetic. So let's say we want to add 5 plus 1, so our final result should be 6, right, in decimal. So 5 is represented by 0, 1, 0, 1, and 1 is represented by 0, 0, 0, 1. So it works much the same way as normal decimal addition does. So we start from the least significant bit and work our way to the most significant bit, with the caveat that each of our digits can only be a 0 or a 1. So in the first case here, we had 1 and 1 together. That gives us a result of 0 with a carry of 1. And then we go on to the next step where we add our carry of 1 with 0 and 0. And that gives us a result of 1. We continue on. We add our next digit, so 1 plus 0. That gives us a result of 1. And then we get to our final place, our most significant bit. So we add 0 plus 0, and that gives us a result of 0. So our final result is 0, 1, 1, 0, which is equal to 0 times 2 to the 3, plus 1 times 2 to the 2, plus 1 times 2 to the 1, plus 0 times 2 to the 0, which is just 4 plus 2, so 6. Exactly what we expected to happen. Now a good question is, can we add positives and negatives together? And the answer is yes. We of course can. It's a great thing about this sign representation that we have. And in fact, this is often how we implement, say, subtraction. So instead of doing, say, 5 minus 1 as an operation, we'll do 5 plus a negative 1. So we'll take the 2's complement of 1, and we'll add that to our value 5. Okay, so let's go ahead and see how that works. So again, we're going to go through this process of adding the individual digits, starting from the least significant bit. So 1 plus 1 is 0 with a carry of 1. We go to our next digit, we add our carry of 1 plus 0 plus 1, which gives us a result of 0, and another carry of 1. Then we add these three numbers together, or carry plus our two digits. So 1 plus 1 plus 1 is 1 with a carry of 1. And then we add our final place, right? A carry of 1 plus 0 plus 1, which is 0 with a carry of 1, right? But what exactly do we do with this final carry here? Now we only have a 4-bit number here. So what we do with this final carry is we just throw it away, right? We just completely discard it, and we never think about it again, because we actually already have a result, right, in these 4 bits. So 0, 1, 0, 0 is just 2 to the 2, right, in the single place here, which is 4. Our expected result of adding 5 and negative 1, right? So that's what we end up doing here. We just end up throwing away this extra carry bit. Okay. Now there are some important considerations to think about whenever we're doing arithmetic with these binary numbers, because we're always talking about things, typically with a fixed bit length, right? Because our computers at the end of the day, everything's in hardware, right? We have a limited number of bits, say, for every operation and what we have for storing things in memory. So it's important to think about our limitations in terms of bits. So for example, can we add negative 4 and negative 4 and get the desired result? And we have the great computer architect and performance engineer answer of, it depends. So the answer is yes, this works in 4 bits, right? Because we can represent negative 8, so negative 4 plus negative 4. We can represent that in 4 bits, right? That's just 1, 0, 0, 0. but we can't represent that in 3 bits, right? So while we can represent -4 in 3 bits, we can't actually get the value of -4 plus -4, right? We need at least 4 bits for that result. So we have to think back to what the range of values can we represent in some number of n bits. And the same thing goes for, say, the product of 2 4-bit numbers, right? So can the product of 2 4-bit numbers fit in 4 bits? So let's think about it from an unsigned case. The max value we can represent in 4 bits in the unsigned case is 15. So, theoretically, we could have 15 times 15, right? Product multiply 2 4-bit numbers together. That result's going to be 225. That clearly isn't going to fit inside of 4 bits. So in fact, for multiplying these n-bit numbers together, we often need 2 n bits, right? In order to store that result. So we have to think about not just, say, how many bits we have for inputs, but how many bits do we need for our outputs, right? What range of values could this operation lead to, right? And can we represent that in some number of n bits? Okay, so that's going to go ahead and do it for this time. A basic introduction to some arithmetic with our binary numbers. There's, of course, a ton we could talk about here, but we're not going to focus on it in this series. But I would encourage you to look up things like how we do binary division and multiplication and operations like that. I think it can be very interesting, especially if you're interested in computer arithmetic in general. But that's going to go ahead and do it for today. As always, I'm Nick, and hope you have a nice day.